Welcome everyone to Zahid's data mining channel once again. My name is Zahid Islam, and today I'm going to present a technique for imputing missing values, right? So we are going to present this paper, missing value imputation, using fuzzy clustering based expectation maximization approach. This is an example dataset, a toy dataset. Here we have four variables: age, education, salary, and position, and 15 records, R1, R2 up to R15. Some of the values you can see shaded, means these values are missing. When you have access to this dataset, you do not see the actual values for these attributes, for these values, for these records. Now, when you have situation like this, they call it missing values, dataset with missing values, and for various reasons you may need to actually guess the actual values for these missing values. For example, for carrying out data mining tasks also, if you have a dataset with missing values, then you may not get as good data mining results. For example, classification results, prediction accuracy, etc., knowledge discovery, etc., as if they were not there, if the values were available. So that for that reason, for many other reasons, for example, for making a decision making, a strategy making process, etc., you may need to actually impute those values. So that's the reason why missing value imputation is a popular research area. I have also presented a few other videos on missing value imputation on my channel. A video on a technique called SIMI, a video on a technique called FIMAS, and also some freely available software. So please feel free to watch those videos on missing value imputation if you want to make it a better understanding, clearer understanding, and also want to see what are the other possible approaches for missing value imputation. There are many other also existing approaches for missing value imputation. For example, expectation maximization imputation is one of them, which uses an equation like this, where this xm is the vector of missing values, mu m is the mean of the missing values for other records where these attributes are available, these attribute values are available, and etc. So this equation then imputes the missing values of a particular record. But we have seen from our other videos, and also if you read the paper that I'm now explaining, you will see that we have argued that this technique and this equation will give you the best imputation result when the records are very similar to each other, and also the correlation among the attributes are very high. Now, as you will agree that the correlation among the attributes cannot be changed. I mean, we cannot change the correlations. It is whatever it is. So it is what it is. So we cannot actually change the correlation among the attributes given a data set. Now, what we can do is we can find out a particular horizontal segment within the whole data set where correlation among the attributes can be higher. For example, age and height, two variables, the correlation overall in the whole, say, population of Australia, the correlation may not be very high. But if you only consider school students who go to school, that is from age, say for example, below 18, then maybe for this group, maybe correlation between age and height can be high. So it is possible to find out horizontal segments of a dataset where maybe the attributes have higher correlation. If you have seen our previous videos, in our previous technique, SIMI and DMI, we tried to find out these type of horizontal segments through decision trees and forests, and we showed that records belonging to one leaf generally are similar to each other, and also the correlation among the attributes among those records are generally higher than the overall correlation in the whole data set. Now, therefore, in those techniques, we used decision trees and forests to actually find out this type of horizontal segments. However, sometimes a dataset can be fuzzy in nature. This is an example of a fuzzy data set. It's a two-dimensional data set, X variable and Y variable. That's why we can plot it in a two-dimensional plane, on a two-dimensional plane. And these dots are representing records, right? So now in a fuzzy data set, the cluster boundaries are not clear. Say, for example, if you consider this is a cluster, then why the records just outside this boundary will not be considered as member of this cluster, whereas the records inside the boundary are considered to be member of this cluster. So this is fuzzy, right? So there is no such clear separation between similar records and dissimilar records, something like that. So in data sets like this, it can be difficult to apply an existing approach to find out records which are very similar and which are very dissimilar in a way like they are not crisp. So therefore, for this type of data sets in this paper, we are proposing to apply a fuzzy clustering technique to find out the fuzzy clustering solution, and then we are proposing to modify this expectation maximization algorithm or this expectation maximization equation to adjust, to accommodate the fuzziness of the data set. If you run a fuzzy clustering on a fuzzy data set, something like this, then for every record Rx, if there are k different clusters, you will get k different association or membership degrees. So every record Rx has some sort of association with every cluster, but then the record may be more associated, more close to one cluster, but less close to other cluster, but still there is some association degree, membership degree they call it, right? So these are the membership degrees of record Rx with cluster 1, cluster 2 and up to cluster K. So in this paper, we first apply an existing fuzzy clustering technique to find out these membership degrees for every record with all other cluster, with every cluster, and then we modify this equation to this in order to compute the missing values of a particular record one by one. Now, since in a fuzzy clustering system, we consider every record Ri is member of all clusters, right? It has membership with each other clusters. So therefore, we need to modify this equation in a way so that we can impute the missing values of this record Ri considering every cluster one by one. So in this equation here, at the moment, we are considering the kth cluster to impute the missing values for the record Ri. Now in this equation, mu m was the vector of mean values of the attributes that are missing in the record Ri, and these mean values are computed based on all other records where these attributes are not missing. These attribute values are available. Now I can show you how that is being modified to adapt in this fuzzy situation. Here, instead of computing just the means, we are calculating the value. RIP is the pth value of the ith record, and multiplying that with the UIK, which is the association of the ith record with the kth cluster. Remember, we are imputing these values based on the kth cluster. So then when we multiply these two and we keep adding them for all records, and then divide them by the total association of all records with the kth cluster, we get the weighted mean M mu P for the cluster K. So using this approach, we can compute this value, and similarly using this approach we can also compute these means. So this is an approach for computing means, so that can be used in the equation. Once we compute these mean values, they can be also used in calculation or in calculating the covariance between two variables P and Q in the context of the cluster K. So covariance between two attributes, two variables P and Q, can be computed using these mean values, and just we are taking into consideration the fuzziness of the data set. So we are multiplying the membership degrees for each record when we compute the difference of the pth value of that record with the pth mean, and this is how we can modify the existing or traditional covariance calculation to take fuzziness into consideration. And then when we complete computing all of these PQ pairs of covariance, then that can be used to compute B, and then B can be used to compute compute the missing values XM. So therefore, through this equation, then considering the kth cluster, we can impute the missing values, vector of missing values for the ith record, and then we can do it for all other records, impute the missing values of all other records using the kth cluster. Similarly, then we can do it using the jth cluster with the nth cluster, etc. For every cluster, we can get a set of missing values. Now, therefore, at the end, then we now need to find out the ultimate imputation, and this is RIP, the ith record's pth value, which was originally missing, and VIP is the imputed value for the pth attribute for the ith record. The imputation of the pth attribute value for the ith record considering the sth cluster, and s can go to 1 to k because there are k number of clusters. So, and then we can actually multiply the association of the ith record here, IP, ith record with the sth cluster in consideration, and then multiply the imputation based on that cluster, and then divide it by the summation of all the associations. So therefore we get a weighted kind of average based on all clusters, the imputation made by all clusters, and that is considered as the final imputation for the pth value of the ith record. If the attribute that has a missing value is categorical, not numerical, then instead of numerical values, the attribute can have some categorical values like Bathurst, Brisbane, Sydney, etc. So in that case, how do we impute? We cannot, of course, use this expectation maximization approach. That's only for numerical attributes. So in that case, we actually take a voting sort of approach. So we try to find out the probability or possibility of each of the possible values. Say, for example, pth attribute has the value missing, and the possible values are L, M, N, etc. So we first consider the vote or possibility of the value L for the attribute P according to cluster K, and what we do is we just sum up the membership degrees of all the records with the cluster K that has value L for that attribute P, right? For all the records in the data set that have for the attribute P the value L, we just sum up their membership degrees with the cluster K, and then we sum them up, and similarly we do it for all other possible values M and N. Similarly, we repeat this for all other clusters, not just the kth cluster. We also do it for jth cluster, nth cluster, etc. all other clusters, and we compute the vote or the possibility of a value L based on all clusters, the same process, and we do it for all possible values for the attribute P. And finally, then we calculate the ultimate possibility by considering these values for all clusters, cluster 1 to cluster K. So what is the possibility of value being L according to cluster S, and what is the association of this particular record I with that cluster S? So we multiply that, and then we keep on doing it for all clusters. So that becomes the ultimate vote for the value L for the attribute P. And then we do the same thing for other possible values. The value that has the highest vote is then considered as the imputed value. This paper is available freely downloadable from ResearchGate, and you can get the link to ResearchGate paper from my webpage. If you go to my webpage, you can find the link. As always, thanks for